So in this video, we're going to characterize a thermocouple. So the thermocouple here that I have is a K-type thermocouple, and I've wrapped it with some copper tape to a PT100 temperature sensor. And how you measure the sensitivity of a thermocouple is basically just heat it up and measure the EMF across it as a function of temperature. So first off, the EMF is very small. It's about 50 or 40, 50 microvolts per centigrade. So you're only looking at 2-3 millivolts of signal total. So you need a voltmeter with a very small range. And you also need a temperature sensor. So I picked out the PT100 here. And this is the interface for this experiment. So first off, I have the temperature sensor, which is the PT100, and that's going to be plugged in between sen and ground. And the temperature sensor says that the room temperature here is about 26 degrees. The second thing is, how do I measure the EMF generated across the thermocouple? So for that, we're going to use the A3 input of SEELab, which allows you to amplify applied signals using an externally provided resistor. And the formula for amplification is 1 plus 10,000 by whatever the value of R is that you provide externally. So I'm using a 100 ohm resistor. So theoretically, I should get 100 times of gain. But it's not an exact 100 ohms, so we need to measure it first. So let me configure the voltmeter part. So here's the voltmeter configuration. There are two options. One is a 16-bit ADC plugin. I'm not using that. I need to buy that. But this is A3 with manual gain. So first off, let me just plug in the resistor here, and the resistance is 95.88, and accordingly I'll just tell the software that this is the resistor we're going to plug in, and the gain that will be applied is 105.29 times. I'm going to take this and put it between RG and ground, effectively applying the gain here. Now with this gain applied, I need to calculate the offset. So for calculating the offset errors, so offset errors come in because op amps have small offsets, and when you apply such large gains for normal op amps, the offsets are also multiplied by that much, and you need to subtract them. So first off, I'm going to ground A3, so it becomes stable, and note down the offset. So this was actually previously noted down, that's why the values were already there. You don't need to keep doing it every time. If you use the same resistor, it just needs to be done once. Okay, so now that is done, and we have 0 EMF at, I need to now put my temperature sensor back in place. So between sen and ground, we have the PT100, and between ground and A3, we have our thermocouple, which are both wrapped together now. So now how do we make the measurements? So there's a start measurements button here, and this will automatically add a data point every 1 degree centigrade. So you can change this. So every 1 degree centigrade of change in the temperature, it will just add 1 point. But you can also add data points manually. So let's look at the automatic mode first. So here I have this hot air blower, which is used for desoldering purposes. And this is what I'm going to use to heat up these two devices. I need to be careful to not heat them up very quickly because I want both of them to have the same temperature. So gradual changes are better. And let's just start measurements and see what the limitations are with this particular setup. Okay, so we started measurements, and I'm just bringing the blower a little close to this. And hot air is coming out from the blower, so temperature is going to start changing. Yeah. Now both of these things are getting heated up, and already you can see that there is a small staircase pattern appearing. So the staircase is a result of the limitation of the sen input used for measuring resistance. Because the value of the PT100 is about 100 ohms, the step size of sen around 100 ohms is only like an ohm or two. So the PT1000 is a better choice, where you'll get, but you won't get the staircase pattern, you'll get much finer resolution. But this should also do, like let's get a full data set, maybe up to 80 or 100 degrees, and see how things look. So this is gradually heating it up. Just fix this here. Temperature is climbing, 60. Maybe I should take a little closer. Okay, now I think I can pause measurements. So this is what the results look like. I have temperature on the x-axis and the EMF along the y-axis. All right, so this is obviously an error here. It should be in millivolts. Since that will be fixed very soon. Okay, so I have this graph here. Now, what I can do is I can just select a reliable region of this graph and say linear fit. So this will fit this data to a standard, well, straight line equation. So it does that, and then it tells you that the slope is 40.2 microvolt per centigrade. So the actual value for a K type is about 41. So we're very close, and this is the intercept. So if you just divide this intercept by this, that'll tell you how far away the room temperature is. So the room temperature is actually about 25 according to this, if you just extrapolate this graph. So I think that brings us to the end of this video. There's not much else to it. Of course, you can reset the data and go and start measurements again. These fields will be filled out automatically when you fit the data. You can save your data. On the left, you have a spreadsheet sort of view of the individual data points that you took. If you wish to export them to, let's say, calc or something and fit them yourself. You can also manually add data points in case you're not happy with this 1 degree centigrade setup. And yeah, thank you for watching.